Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we'll extend our discussion on thermal properties of materials. So far we have discussed various basic concepts related to heat, temperature, specific heat, heat capacity, specific heat, molar specific heat, water equivalent, all that. So in this video we are going to discuss about another important concept which plays a very important role, especially for material science and engineering, for the selection of appropriate engineering materials, which is thermal expansion of materials. Okay, so we'll do that, we'll study that. So the basic principle here is that almost all solids, liquids and gases, they expand on heating. Okay, they expand on heating, they increase their shape, their size in terms of length, breadth, height, diameter, whatever the dimensions changes, it increases with increase in temperature. So this increase in the dimension or size of a body when it is heated, that is temperature is increased, that is called as thermal expansion. Okay, so what is the reason behind this thermal expansion? What is the cause of thermal expansion? Now we have studied while discussing the basic mechanical behavior of solids, and also while discussing heat and temperature, that all solids, all materials, they are made up of atoms and molecules. Okay, and they are held at certain equilibrium separation distance. Okay, the minimum equilibrium separation distance. Every object, it has atoms and molecules, and they are naturally in undisturbed position when there is no external force. They are at certain minimum equilibrium separation R0. Now when they are subjected to heat, when heat energy is supplied externally, the amplitude of these vibrations of atoms or molecules, that increases. We discussed in the first video that heat is nothing but the internal energy content of the solids because of their atomic or molecular movements, translational, rotational, vibrational. So when heat energy is supplied, these kinetic energies, it increases, and the average interatomic separation also increases. See, this is the natural equilibrium separation, and when it is increased, they start vibrating with much higher energy. Their kinetic energy increases, the vibrational energy increases, and their separation gap also increases. Okay, this. So as more and more heat is supplied, always remember this is there is to and fro movement. So when more and more heat is supplied, the vibration becomes more and more, and this causes increase in the dimension of the object, whether it is in terms of length, breadth or height, whatever it is, there is thermal expansion of the solids. So this is strictly for solids. Okay, for liquids and gases there are different concepts. This is only for solids. Okay, so there are different types of thermal expansion. One is only in terms of length, in one direction, so it is called as linear expansion. Another one is in terms of area. Okay, Here it is one dimensional, only in one direction, one dimension. This is two dimensional in two ways, length breadth or breadth height or height length, like that. So there is change in area or increase in area. Another one is volume or cubical expansion. This is in terms of volume, which is three dimensional. There is change in three dimensions, length, breadth, height, x, y, z axis, both. I mean all three are involved. So we'll discuss them one by one. So first, linear thermal expansion. So linear thermal expansion is the increase in the length of an object because of application of heat. Let us say we have a metallic rod which is at an initial temperature of Ti and it has a length Li. Initial length Li, initial temperature Ti. Suppose it is subjected to heat, and because of the application of heat, the temperature increases to Tf, the final temperature Tf. So the length of the rod, it will increase from Li to Lf. Let me use a different ink. From Li to Lf when temperature is increased from Ti to Tf. So here there are certain important things. First, what is the increase in temperature or the change in temperature? That is final temperature minus initial temperature. What is the change in length or the increase in length? That is final length minus initial length. So here there is an equation that governs what will be the relationship between this change in length and change in temperature and what other parameters are involved. How all these are interrelated. So the change in length delta L, the degree of change in length of the material in response to the change in temperature delta T, is given by delta L is alpha Li delta T. So here it says that the change in length is directly proportional to the initial length. The change in length is directly proportional to the increase in temperature. When we combine these two, it becomes delta L is equal to alpha Li delta T. Here alpha, don't confuse proportionality with alpha. This is alpha symbol, this is proportionality symbol, okay? So this alpha is the linear thermal expansion coefficient, okay, this. So the change in length is equal to alpha Li delta T. So the final length is equal to Li, that is the initial length, plus the increase in length. So that is equal to Li plus alpha Li delta T, which is expressed as this. Alpha Lf is equal to Li into 1 plus alpha delta T. Li is taken common. So now the thermal expansion coefficient, it can be expressed as the linear expansion coefficient as here from this. Delta L is equal to alpha Li delta T. We can write it as taking this much portion to the denominator. Will it get delta L by Li delta T, or Lf minus Li by Li delta T. That is the linear expansion coefficient. Now as you can see, in both the numerator there is length Lf minus Li, which is in terms of meter, centimeter, whatever it is, and here also there is length. So they get cancelled out, so we have only temperature, degree Celsius or Kelvin inverse. These are the units of linear expansion coefficient. Okay, so always remember here the increase in length, it depends on two parameters, the initial length and the change in temperature. Okay, so the more the initial length, the more will be the increase in length. The more the change in temperature, the more will be the increase in length, because there is direct proportionality relationship here. So this is linear thermal expansion. Then we have surface thermal expansion. Surface thermal expansion is increase in surface area. So let us say we have an object of initial surface area Ai at initial temperature Ti. Then it is subjected to heat so that the temperature increases from Ti to Tf. So here the change in temperature is final minus initial. At temperature Tf, the surface area increased from Ai to Af. Okay, surface area increased. So the increase in surface area is equal to Af minus Ai. Okay, so here there are two things: change in temperature, change in surface area. So here the increase in surface area is similar to change in length. Here the increase in surface area is directly proportional first to the initial area and second to the change in temperature, which is equal to Tf minus Ti. So combining these two, we get the increase in surface area is equal to beta Ai delta T, where beta is the proportionality constant, which is surface thermal expansion coefficient. So here the increase in surface area is directly proportional to the initial area, and it is also directly proportional to the change in temperature. So the more the initial surface area, the more the increase in area. The more the increase in temperature, the more the increase in area, because direct proportionality relationship. Similarly, as we did in linear thermal expansion coefficient, the final area can be expressed as Ai, that is initial area, plus increase in area, which is equal to Ai plus beta Ai delta T from here, and then we take Ai common, so we get Af is equal to Ai into 1 plus beta delta T. So the superficial, it is also called a superficial expansion, surface expansion or surface area expansion. So this coefficient, it can be expressed as this. From here, if we take Ai delta T to the denominator on the left hand side, we get beta is equal to delta A by Ai delta T, or which is equal to Af minus Ai by Ai delta T. Again, both in the numerator and denominator, this is area, Af minus Ai, and Ai is also area. So this get cancelled out and we have only temperature in the denominator. So again the unit is degree Celsius inverse or Kelvin inverse, same as linear expansion coefficient. Then we have the final expansion, which is volume expansion. Okay, in terms of 3 dimensions. Length is 1 dimension, surface area 2 dimension, volume 3 dimension. Let us say we have a material which is at an initial temperature Ti and it has an initial volume Vi. It is subjected to heat so that the temperature increases from Ti to Tf. As a result of this heat application and increase in temperature, the volume will increase from initial volume Vi to final volume Vf. Here also there are two things. First, the increase in temperature Tf minus Ti, that is equal to delta T, and the increase in volume, which is equal to Vf minus Vi. So here also the increase in volume, it depends upon two things. The increase in volume is directly proportional to the increase in temperature, and the increase in volume is directly proportional to the initial volume. So if we combine these two, we get the increase in volume is equal to gamma Vi delta T. So here gamma is the proportionality constant, which is the volume expansion coefficient. Again, here the increase in volume is directly proportional to the increase in temperature and to the initial volume. So the more the initial volume, the more the increase in volume there will be. If the more the increase in temperature, more higher the temperature increase, the more the increase in volume, because they are both directly proportional to each other. And gamma is the volume expansion coefficient. So the final volume is given by Vf is equal to Vi plus increase in volume delta V, which is equal to Vi plus gamma Vi delta T. And if we take Vi common, we get this expression. Vi is equal to 1 plus gamma delta T. So if you see in all of these expansion equations and their formulation, the basic core concept is the same, their format is the same, their structure is the same, just we are replacing length with area with volume, that, but the core structure is the same. The overall structure of the equation, the overall concept stays the same. The change in dimension is directly proportional, whatever dimension it is, the change in dimension is directly proportional to the change in temperature, and the change in dimension is directly proportional to the initial dimension. This dimension can be length, it can be area, surface area, it can be volume, it can be whatever. Okay, the basic structure is the same, and then there is a proportionality constant associated with that dimension. For length it is linear expansion coefficient, for surface area it is surface expansion coefficient, for volume it is volume expansion coefficient. And similarly we can calculate the volume expansion or cubical expansion coefficient as this. From this equation, if we take Vi delta T to the denominator on the LHS side, we get gamma is equal to delta V by Vi delta T, where delta V is equal to Vf minus Vi by Vi delta T. Again, volume is there in the numerator, volume is there in the denominator, Vf minus Vi, they have the same units, so they get cancelled out, and we have delta T in the denominator, so these are the units. Degree Celsius inverse, Kelvin inverse. Same as linear and surface area expansion. Then there are some important relationship between expansion coefficients. Here I have not done the derivation. For derivation you can see the thermodynamics playlist. I have not included derivation here because it is not required. I mean, if you want it I will do it, but for now it is not that much required for material science, the derivation. So you need to understand the relationship between the expansion coefficients. So first, the relationship between the surface expansion coefficient and linear expansion coefficient, okay, area and length, the relationship. So beta is equal to 2 times alpha, beta is equal to 2 alpha, okay, twice the linear expansion coefficient. The surface expansion coefficient is twice the linear expansion coefficient. Similarly, the relationship between volume and length, that is volume expansion and linear expansion, that is gamma is equal to 3 alpha. So if we combine these two, we have the relationship alpha is equal to beta by 2, which is equal to gamma by 3. Okay, so here from here we have alpha is equal to gamma by 3, from here we have alpha is equal to beta by 2. So alpha is equal to beta by 2 is equal to gamma by 3. Okay, so we can say beta is equal to 2 by 3 gamma, or gamma is equal to 3 by 2 beta. Okay, so anyway you want to remember it, it's your choice, but this is the general relationship between expansion coefficient. If you want derivation, You can ask, I will provide a separate video for that if you want it. But also you can watch the thermodynamics playlist also. I have there I have gone into detail. Like I said, here we will just brush the important things that are required for material science engineers. This is basically thermodynamics, heat and temperature, that field. But like I said, every department of engineering science, it has some interrelationship between them, because everything is derived from the other. No thing can exist in isolation, complete isolation. There will be some interrelationship. Okay, so this much is required. So these are some of the thermal expansion coefficients of materials. I have included only the linear expansion coefficient. From this you can calculate the other two using this formula. So again, these are approximate values. You cannot go for accuracy and precision here. These are approximate values, okay? So we have for aluminium here, the expansion coefficient is in terms of 10 to the power minus 5 Kelvin inverse. So whatever it is, you multiply it with 10 to the power minus 5 Kelvin inverse. So aluminium is 2.5, brass is 1.8, iron is 1.2, copper is 1.7, silver is 1.9, gold is 1.4, and glass, basically it is Pyrex glass, that one, so it is 0.32. So these are some of the approximate values, okay, of materials. You can calculate beta and gamma for these using this formula if you want. So this is basically the concepts related to thermal expansion of solid materials. Okay, so this is the thing.